Welcome to Visual Algebra Lecture 3.7, Products of Subgroups. We'll begin this lecture by understanding when the product AB of two subgroups, A and B, is a subgroup. One sufficient condition is that one must normalize the other. If AB isn't a subgroup, then it's an algebraic object called a double coset. We will state without proof several basic properties of double cosets. The proofs require group actions, which is the topic of Chapter 5. However, it will serve us well to understand them now and to explore some examples. In particular, the AB double cosets partition the group, but they need not all have the same size. We'll see examples of this in the dihedral groups D3 and D4, the symmetric group S4, and the alternating group A5, and this will help us understand subtle but crucial structural properties of subgroup lattices that we would otherwise probably miss. Let's get started. Thus far, we have seen a number of definitions that involve a product of elements and a subgroup. And for all of these, the notation is indicative of how it's defined. For example, the left coset X times the subgroup H is the set of all products of the form X times an element H in the subgroup. And the right coset is defined analogously, but X goes on the right. A conjugate subgroup, XH X inverse, is just the set of all products X little h X inverse. We can also define the product of two subgroups, A and B, in this manner. We write A times B, and it's the set of all products of elements, little a times little b, in the respective subgroups. But it's worth emphasizing that this need not be an actual subgroup. Let's investigate when this is a subgroup, and we'll use D3 as a motivating example. So here are two Cayley graphs with different generating sets. I think it's helpful to see both of these. And this is a triangle. F, or S, is going to be the reflection across this vertical axis, and then T is FR, which is the reflection across this other axis. And we can check that if you do F and then, or S times T, that's F squared times R. So in other words, ST equals R, which is a rotation. So let's let A be the subgroup generated by S, and B the subgroup generated by T, and C the subgroup generated by ST. And we'll consider AB and AC. Let's start with A times B. So A times B is, well, let's write out what A is. A is 1 and S, and B is 1 times T. So if we take all products of things in A with things in B, we get 1. We get 1 times T. So 1 times 1, 1 times T, S times 1, and S times T. So that's 1T, S, and ST. And that is certainly not a subgroup because it has order 4. And then if we take AC, this is, well, C is the 3 rotations, so we can write that as 1 ST TS, or it might be easier to think of this as 1 R squared. I think for this one it's easier to use this generating set over here. So something in A times something in C, we have 1 times 1, 1 times R, and 1 times R squared. So right away we get all 3 rotations, 1 R and R squared. And then we have S times 1, which is, or we can think of this as F. So F times 1, F times R, and F times R squared. We see right away F, FR, and FR squared, that we actually do get all of D3. So A times C is the entire group, definitely a subgroup, whereas A times B is not a subgroup, it's just a set of 4 elements. What's going on? What do you think? What do you think the criteria is for a product of two subgroups that be another subgroup. If AB is a subgroup, well then obviously it must be above A and B in the lattice, or at least as high. It's equal to A and B if these are the same. For closure to hold in AB, which is a requirement of it being a subgroup, then we need that the product of two elements in AB, let's say A1B1 and A2B2, has to lie in AB. But this need not happen. Well, if B1A2, let's look at these middle two elements. If B1A2 equals A2B1, in other words, if these commute, then this product, A1B1 times A2B2, is just A1A2 B1B2, and this lies in AB, and we're done. But we can't always guarantee that to happen. So here's a weaker condition that will have the same result. So let's suppose that B1A2 lies in AB over here. That means that B1A2 equals some A3B3. Can't guarantee they're the same element. And then A1B1 times A2B2 equals A1B3. Sorry, A3B3, A2. We're just swapping these two elements like that. And now we are living in AB, and we get the same conclusion. I'm going to actually show you that we don't need to change, or I'm going to show you a condition that if it holds, we don't need to change both of these elements to different elements. We're going to actually just let A2 equal A3. In other words, we can swap the order of these if we change one of them. Let's see what that condition is. I claim that if A is contained in the normalizer of B, in other words, A normalizes B, then the condition we just looked at will hold. Let's understand this. So if A normalizes B, that means every left coset of the form little a times B is a right coset B times little a. And that means that this left coset, which is a set of elements of the form little a times little b, is the same as the set of elements of the form b prime times little a. Now a is fixed here, but b and b prime get to range over the entire subgroup. So that just means that everything that I can write as AB can be written as something else in B times A. In other words, everything in every element of this, AB, which is in big A times big B, can be written as this over here, which is in big B times big A. So to see this, now suppose A normalizes B. Then this product that we had up here, we can take this B1A2, and we can swap the order of that and write A2 times B1 prime for some possibly other element in B. And now we have the product of elements in A times elements in B. Let's state this as a proposition. If A and B are subgroups of G, and one of them normalizes the other. Up here I said A normalizes B, but by symmetry, the same conclusion would hold if B normalizes A. We would just swap the roles of the element in the subgroup here. In that case, AB is a subgroup of G. Let's sketch a proof of this, or outline it. So we got to show the three properties of a subgroup hold. First, the identity. Well, E times E is definitely in A, B, because both A and B contain the identity, and that's the identity. So AB contains the identity. Closure. We just did that. We take the product of two elements in AB and we get something in AB. So the only thing we haven't checked are inverses. So let's take little a, little b, and big A, big B. Then AB inverse is just B inverse A inverse. And, well, by this argument up here, everything that we can write as something in A times something in B is something in B times something in A. In other words, if this holds, then AB equals BA as sets. And, well, if BA contains the inverse of this, then so does AB because they're the same. Now, realistically, we don't use this condition that much about one of these things normalizing the other. The more common thing to notice is that if you have, a more common thing to use is that you might have two subgroups, A and B, and one of them is normal. If that happens, then automatically AB is a subgroup. Because if one of them is normal, that just means everything normalizes it. The normalizer is the entire group, so it will contain the other one. A quick word of warning. It may still happen that the product of two subgroups equals G, even if neither subgroup normalizes the other. What we were really getting at in this condition was that AB had to be equal to BA. As an example, let's take S4, whose subgroup lattice is shown before, and let's take the subgroup A over here, so just one of the D4 subgroups, and let's let B be one of these S3 subgroups. Now, we don't quite have enough tools to know the conjugacy classes of S4. We'll have this in a couple of lectures. I will tell you that these three subgroups are conjugate, as are these four. And therefore, neither of these are normal. And that means that the normalizer of both of them, well, it can't be the entire group, because that happens only when it's normal. And there's nothing in between, so that means that the normalizer of both of these has to be the subgroup itself. So if the normalizer of both B and A are themselves, then the normalizer of A does not contain B, and the normalizer of B does not contain A. But you can check that, maybe it's a little tedious, that the product AB is indeed the entire group S4. We'll come back to this example before the end of the lecture and understand why this is true without having to actually check this by multiplying out all of the elements. And the key to doing that is with the following definition. If A and B are subgroups of G and X is some element, then an AB double coset is a set of the following form. We write AXB, and that is, by definition, the set of all products of elements, little a x times little b, where little a and b are in their respective subgroups. At this point, I want to state a handful of basic properties of double cosets with the caveat that we don't yet know how to prove them, the missing piece being group actions, the topic of Chapter 5. Though it's a bit risky to state results without proving them because there might be a circular argument, we're not going to use any of the results that I list here other than to just illustrate examples which will help us understand the structure of subgroup lattices better. Well, first of all, notice that the product of two subgroups A, B is always going to be a double coset for the element X being the identity. Now, there's a basic theorem that is proven in most algebra courses that says if A, B is a subgroup, then the size of A times the size of B divided by the size of A intersect B is the size of the product AB. And I would commit this to memory. I don't think it's too unreasonable to memorize. But this holds even if AB is not a subgroup. In other words, it holds for double cosets, not just subgroups. And where this comes from or how this is proven is, well, the size of A divided by the size of A intersect B is just the index of A intersect B in A. But I don't memorize this. I just memorize this one right here. Next, the double cosets define an equivalence relation. We say that X is equivalent to Y if and only if X is in the double coset A, Y, B. This is analogous to what we said for regular cosets. We said that we could say that X is equivalent to Y if and only if X is in the coset Y, B. Remember that? Because in this case, XB equals YB. As a corollary, G is the disjoint union of its AB double cosets. The fact that this defines an equivalence relation means that double cosets are disjoint. Equivalence classes are always disjoint. And notice that every element Y in the group is in a double coset. It's in A, Y, B, because in this group, or in this double coset, is the element E times Y times E, which is equal to Y. So not only are the double cosets disjoint, but they partition the group G. Next, the double coset AXB is the union of left cosets of B. Let's see. Okay, now why is that? So what is AXB? Well, let's say that A, which is a collection of elements, it doesn't have to be finite, but let's just say it's E, which is, let's say A2, A3, up to AK. Well, then this double coset is just, it's E times XB union A2 XB. I mean, it is the set of all things of the form something in A times X times something in B. So everything in here is going to be in one of these cosets, which are not necessarily disjoint. A3XB union all the way up to AKXB. Convince yourself that, again, everything in here can be written in here. But how many cosets are there? Some of these are not necessarily disjoint. That's the other part of this. It says that the number of left cosets, disjoint left cosets that make up this is this index right here. So it's the index of A intersect a conjugate of B with A. Now, I don't expect anyone to look at this and really understand why this is what it is. And I think it's one of those proofs that follows notationally once you learn about group actions. But the take-home message should not be this exact formula. It's just that this is the union of some number of cosets. But if we have this formula, which we will be able to do in chapter 5, then we know the size of this. So in that case, let me just draw a little picture. If this is the double coset AXB, then what that means is AXB is the identity times X times B times A2XB up to A, say, KXB. So if we know that there are exactly this many cosets, and we know that the size of each coset, the size of each AIXB, that's just a coset of B. That's got the size of that is the size of B. Then the size of this double coset is just the size of B times the number of cosets, which is just this product here. So this gives us a formula for the size of double coset. And here is that formula slightly cleaned up. The size of a double coset AXB If we use Lagrange's theorem and write this thing as the size of A divided by the size of A intersect XB X inverse, then notice that this is indeed a generalization of this up here. And once again, I don't worry about this as much as this right here. If you take X to be equal to the identity, then this formula here just becomes this right here, which I told you to memorize. And we'll do some examples of this with subgroup lattices. Let's do some examples. First, let's start with D3, which we saw earlier. Let's compute the double cosets of the subgroups A and B, where A is generated by RF and B is generated by F. So I think this is different A and B than I did in the first slide. Doesn't really matter. So let's say that this is A right here, and this is B. So there's two elements in here, and there's two elements in here. So there's four products we can make. 1 times 1 is 1. 1 times F is F. RF times 1 is RF, and RF times F, see, that's RF times F equals RF squared, which is R. So we get four elements right here. And so to find the other double coset, take something that's not in here, let's say R squared, and write AR squared B. And now this is all things of the form something in here times B. So let's write this out. This is 1 times R squared times 1 equals R squared. 1 times R squared times F equals R squared F. So I'm taking 1 times R squared times something in here. And then let's take RF times R squared times something in here. So RF times R squared times 1 equals, let's see, so remember we can write FR squared as RF. So that's R times RF, which is R squared F. And then we have RF times R squared times F. Let's just do that over here. So RF R squared times F, which is R squared. So yes, these four products just give us two elements. And here's the partition into double cosets. This is A, B right here, and this is A, R squared B right there. Notice that there's two cosets in this double coset, or two cosets of B, and there's one coset of B right here. So remember that the size of A, so let's go back over here. The size of AB is just the size of A times the size of B divided by the size of the intersection, which is 1. So right over here we can say that the size of AB is 2 times 2 over 1, which is 4. And then what about this one here? The size of A R squared B is this 2 times 2 divided by, now what do we have? We have, what is R squared? So let's see, what is R squared B R minus 2? You know, this is R squared times B is subgroup generated by F, R minus 2. So let's check. R, F minus R minus R, that is RF, and that is equal to A. So the size of this is, maybe I should write this out, is the size of A times the size of B divided by the size of A intersect A, because this is conjugate is just A. So that of course is just A. So this is 2 times 2 over 2, and that's equal to 2. So the idea is with these double cosets, we take A and B, and then we say, as we what are the possible conjugates of B? As we conjugate B, it might go to one of these things. And what are the possible sizes of the intersection here? If these are different, the intersection is trivial. If they're the same, then the intersection has size 2. So the only cosets are going to, double cosets will have size 4 and size 2. Let's do this again, but now with D4. So I'm going to let A be the subgroup generated by r squared f, and B the subgroup generated by f. So before we do any computations, let's just compute the size of A times B. So the size of A times B is going to be the size of A times the size of B over the size of the intersection, which in this case is going to be 2 times 2 divided by 1, which is 4. So indeed, if we do A times B, let's see. Let's write it down here. AB equals 1 times 1, 1 times f, r squared f times 1, and r squared f times f, which is r squared. So we get 4 distinct elements, 1f, r squared f, and r squared. Right here, those are the following 2 cosets. There are 2 left cosets of B, right there. What else? So let's take an element that's not in this double coset. Let's say R, and let's compute A, R, B. So first of all, before we do this, let's see what sizes it is. So A, R, so the size of this down here, let's see, let's write it up over here. So the size of A, R, B is the size of A times the size of B divided by the size of A intersect. Now what is, I'll do it up in the corner, R, B, which is generated by F, R inverse. So R, B, F, R inverse is R squared F. So that is a subgroup generated by R squared F, and that is equal to A. So the size of this is going to be A intersect A, and that's going to be 2 times 2 divided by 2, which is 2. So indeed, you can check there's only 4 elements, or 2 elements that you get by multiplying. So let's see, something in here times something in here with R in front, so R in middle. 1 times R times 1 equals R. 1 times R times F equals RF, and we can stop. I mean, we could write R squared F times R times 1, and R squared F times R times F, and we can check what this is. R squared F times R is RF, and the other one better be R. Let's check. R squared F, R, F is R. So here is the next coset. It's this next double coset, and then I won't do it, but you can check that. The last one is going to be this coset. The last double coset is going to be just this single coset. One straightforward but important remark that I want to emphasize, which follows immediately from this equality here, is that if the size of A times the size of B is bigger than the size of the group G, then the intersection of A and B cannot be trivial. It has to have size bigger than 1. And why does that matter? Well, to me anyways, that gives some extra insight about the structure of subgroup lattices. And let me show you what I mean by that. Let's return to the symmetric group S4 and see what we can deduce about the subgroup structure just by this property that the size of AB, whether it's a subgroup or not, is the product of the sizes of A and B divided by the size of the intersection. First of all, I want to draw a line across here. Let's where am I going to put it? Right here. And notice that everything above this line are the orders 6, 8, 12, 24. The square of these is bigger than S4. So what that means is, well, let's start with an example with these S3s. Let's suppose that A and B are both copies of S3. Then the size of AB is 6 times 6. And right away, we are bigger than 24. So we know automatically that any two subgroups, intersection of any two subgroups that are S3 has to be non-trivial. And in fact, they do intersect in C2. So this divided by 2 equals 36 divided by 2 equals 18. So in other words, the double coset AB, well, AB cannot be a subgroup because there is no subgroup of order 18. That doesn't divide 24. But this double coset has to have order 18. And just more generally, if we take any pair of subgroups above here, say a D4 and an S3, or a D4 and an A4, or two D4s, because of this result here, they have to intersect non-trivially. And that, again, this is a structural property of subgroup lattices. As we get higher up in the lattice, two large-ish groups cannot intersect trivially. What else does this say? Let's take two C3 subgroup. Let's take I'm going to reuse A and B, but use different colors. Suppose A and B are both C3 subgroups. Then the size of A, B is 3 times 3 divided by intersection, which is 1, which is 9. So we know that the product of any two of these cannot be a group. It's a double coset with size 9. What else can we say? Let's take A to be one of these C2s and B to be another C2, but not the adjacent one that sits in the side, the same V4. If we do this, well then the size of, in this case, the size of A times the size of AB is the size of A. Let's just write this down as 2 times 2 divided by the intersection is 1, which is 4. So if it's a subgroup, it's got to be an order 4 subgroup that contains both, but there is none. So this cannot be a subgroup. Let's do one more of these, though I don't know how much it adds. If we let A and B be these C4s, or two different C4s, then the size of AB is 4 times 4, and then they intersect trivially. Divided by 1, which is order 16. So this is a double coset of size 16. And then, well, let's see, what are the sizes of the other double cosets? Well, we know that the other double cosets are going to, let's use this formula over here. So AXB for some other double coset is the size of A times the size of B divided by the size of A intersect some other conjugate of B. Well, if some other conjugate of B is say this one, then this is going to be divided by 1, and 4 times 4 divided by 1 would be 16. We can't have two disjoint double cosets of size 16 in a group of order 24, so we have to have something bigger than 1 here, but these all intersect trivially, so that the only way that these A and B, or A and this conjugate of B, is not have size 1 is if they're the same. So that means that these would have to be the same, and we get 4 divided by 4, 4 times 4 divided by 4, which is size 4. So in other words, the double coset partition of S4 by these A and B are going to be 16 plus 4 plus 4, which adds up to 24 elements. So without even computing, we know that this is the size of the partition. And we get that from these formulas and just looking at the subgroup lattices and the possible conjugates of B. So this double coset business is not the most important thing. I don't usually teach it in class, but it's good practice to take what we've done so far and to practice conjugate subgroups and intersections and just getting fluent with these subgroup lattices. Let's finish with the alternating group A5. And I won't spend as much time on this one, but once again, I'm going to put a line right across here. And so the order of everything above this line is more than the square root of g. So in other words, any two of these d5s we know have to intersect non-trivially, as do any two of these a4s. But we also know that if we take, say, one of these S3s and one of these A4s, that they have to intersect trivially because non-trivially, because 6 times 12 is bigger than 60. And once again, if we had the size of A times the size of B over the size of the intersection A and B, this is 12 times 6. This is 72, right? Again, right now we know that this has to be bigger than 1 because this number cannot be bigger than 60. There are some other things we could say about this, kind of like what we did for S4 last time by looking at different copies of C3 or C2 or C5, but I'm not going to do those. I'll let you explore that on your own. And I encourage you to look at some of the other subgroup lattices that we have seen. And I think the big takeaway is the fact that is this formula right here. And what it really says is that, again, as subgroups get larger and larger, they just have to intersect non-trivially. And that is a basic property of the structure of finite groups and of subgroup lattices. And I hope you remember that going forward. Okay, so this lecture was on products, which is how to multiply subgroups together. And coming up next are quotients. This is how you divide a group by a subgroup. We've been seeing this throughout the course, and we are finally ready to formalize it. So don't go anywhere. I'll see you then.